Okay, I can see your eyes light up by this sight. How many of you had a radial flyer wagon or tricycle when you were young? Hopefully all of you. So let's say that you get a job right after you complete your degree here at the university. You get a job with a radial flyer assembly plant in Chicago, Illinois. And you are hired to oversee the assembling of their wagons. And so you walk into the assembly plant and you're told that you have an 800-pound box of wheels and a 500-pound box of beds and a 50-pound box of handles and a 100-pound box of axles. And the question then is, how many pounds of wagons can you assemble with those components? So you're thinking 800 plus 500 plus 50 plus 100, that's 1,450 pounds of wagons. But then you remember that you took freshman chemistry and you say, no, I've got to think about this differently. I can't just add up the weight of the components. I have to first think about balancing this assembly process as if it's a chemical reaction. Because I need, for every wagon that I assemble, I need 4 wheels, for 1 bed, for 1 handle, for 2 axles to make 1 radial flyer wagon. And besides knowing the mass of each of the components, you know, the 800-pound box of wheels and the 500-pound box of beds and the 50-pound box of handles, etc., I must take into account the weight of each component. And so let's say that you're told then, because you're asking questions, you're thinking about this analytically, that each wheel weighs 2 pounds, each bed weighs 5 pounds, each handle weighs a half a pound, and each axle weighs 1 pound. Okay, now with that information, I can go back. I had 800 pounds of wheels, and each one weighs 2 pounds. So how many wheels do I have? I have 400. Each bed weighs 5 pounds, and I have 500 pounds of beds. And so that means I have 100 beds. And likewise, you could determine that you have 100 handles and 100 axles. Okay, so 400, 100, 100, and 100. All right, that sounds like everything's going to work out fine, right? But I'll look at it a little bit more closely. So if I have 400 wheels, yes, I could accommodate 100 beds, and I could then accommodate 100 handles, but I would need 200 axles, and I only have 100 axles. So you will have determined by using your critical thinking that you can only assemble 50 wagons, because you need 2 axles per each wagon. You can only make 50 wagons. Okay. Now, so we can make 50 wagons. What is the mass of each wagon? Well, we'll go through this quickly, but the mass of each wagon would be 15.5 pounds. So that means I can actually, with all of the materials that I started with, the 800 pounds of wheels, the 500 pounds of beds, the 50 pounds of handles, 100 pounds of axles, I can actually make 675 pounds of wagons. Not a bad day's work, but certainly not just a sum of 800 and 500 and 50 and 100, because we had to take into account 2 things. That is the balanced assembly process, which will be analogous to the balanced chemical reaction, and we had to reduce it not just to the mass of each, but to the number of each of these components by dividing by the mass per, which will be analogous to dividing by the molecular weight to reduce things to the number of moles of each component. That is, this is the same kind of process. The assembling of a radial flyer wagon, taking these factors into account, is exactly the same kind of steps we're going to take to understand stoichiometric problems in chemical reactions. So in the next slides, we're going to talk about the following kind of problems. Problems where one reactant is limiting and the other is in excess. Problems where the reactants are in aqueous solution. We'll see that we have to add a few extra tools to our toolbox. Problems in which we have to determine which of 2 or more reactants is limiting, just as we had to do with the assembly of our radial flyer wagon. Problems where we want to produce a certain amount of product and then have to work backwards. That is, what if our boss told us we have to make 1,000 pounds of radial flyer wagons by the end of the day? and then determine which of the components is limiting, and problems in which we determine the percent yield. Now, some of these examples will involve reactions in aqueous solution, and we will express these in terms of what can be called, in general, titration reactions. This is a common type of chemical problem where you want to determine how much of a reactant A or reactant B is in a solution by titrating a solution with B to determine how much A is present, etc. We will give examples of these involving acid-base titration reactions, precipitation reactions, and oxidation-reduction reactions. So titration reactions are sort of a subset of these stoichiometric problems. Now, a key to a titration reaction is that the reaction should occur fairly rapidly. That is, we don't want to wait all day for it to happen. We'd like it to occur quickly, and we'd like the endpoint to be easily observable. Think about that. If your endpoint is not observable, it doesn't lend itself very much to a titration reaction. For example, in acid-base reactions, we typically observe a color change when the reaction has reached what we call its endpoint. And for precipitation reactions, we perform the precipitation reaction and collect the amount of insoluble material and weigh it to determine the amount of product. That is, we have to have something that we could easily use to determine when the endpoint has been reached or when all of the reactant has been converted to product. Likewise, for oxidation reduction reactions, we'll see that many of these involve color changes. But before going to some of these examples, let's talk about the concept of molarity, because many of these reactions will take place in aqueous solutions. Molarity is a way that we express concentration or molar intensity of a substance using what we call molarity. It's the number of moles of a substance, either the reactant or product, per volume of the solution. Moles per volume. So capital M, molarity, is equal to the number of moles in of any particular solute, which could be a reactant or product, divided by the total volume of the solution. For example, if you have 20 grams of sodium hydroxide and you dissolve it in 2 liters, total volume, 2 liters of aqueous solution, the molarity will be, go ahead and figure it out, you first solve for the number of moles of sodium hydroxide by dividing the 20 grams by the molar mass of sodium hydroxide, which happens to be 40. So the number of moles would be 0.5 moles, and we said that these 0.5 moles are in a total volume of 2 liters. So we then divide by the 2 liters, and we get a molarity of 0.25 moles per liter, or we say that the molarity is 0.25 molarity. Likewise, this relationship is useful because if we know the molarity of a solution in a particular solute and we know the volume, we can multiply molarity times volume to get the number of moles. M times V is equal to N. Now later we will talk about other concentration scales, but for this particular chapter and these problems, we're going to stick with molarity because it's the easiest one to use. So let's launch into our first stoichiometric type of problem so you can see what we're talking about. Let's consider the reaction of nitrogen dioxide with water to form nitric acid. You see the balanced reaction. The balanced reaction is 3 nitrogen dioxides plus water goes to 2 nitric acids plus nitrogen oxide. And let's say that we start with 100 grams of nitrogen dioxide. And the question is, how much nitric acid will we form? Now, when we say how much, we generally mean what mass of. What mass of nitric acid can be formed? How do you solve this problem? Well, just as in our radial flyer assembly process, the 100 grams is not what we need to know. We need to know how many moles of nitric acid, just as we need to know how many wheels and how many beds and how many axles. So we begin by taking the mass, 100 grams, of nitrogen dioxide and dividing by the molar mass, 46 grams per mole, to get the number of moles of nitrogen dioxide, the number of moles of this reactant. Now, the way this problem is expressed, we assume that we have an excess of water. We weren't told anything about how much water is present, so we would then assume that water is in excess. It's pretty cheap. We have all the water we need. So if we determine the number of moles of nitrogen dioxide, how many moles of this product, nitric acid, HNO3, can we form? Well, we have to look up to that stoichiometric relationship. 3 nitrogen dioxides goes to 2 nitric acids. Okay, so if we have 2.17 moles of the reactant, nitrogen dioxide, how many moles of nitric acid can we form? That's right, 2/3 as many, because it has to be in this ratio of 2 products per every 3 reactant. 2/3 as many. Or in other words, we'd form 1.45 moles of nitric acid. But if we were asked how much, what do? To determine the number of grams, we multiply by the molar mass of nitric acid, which happens to be 63. And so 1.45 moles of nitric acid times its molar mass, we wind up with 91.3 grams of nitric acid is formed. Now, does that make sense? So this problem is not so difficult. This is a simple, straightforward problem in which we're told how much of a reactant, we're asked to determine how much product, and we can then assume that all of the other reactants or products are in excess or that we don't care about them. Okay. So let's do a second stoichiometric problem of this type, in which we were told how much of the one reactant we have, and we were asked how much of the second reactant would we need to completely react with the first reactant. Okay. So here is an acid-base reaction, a typical type of acid-base reaction. Ammonia plus sulfuric acid going to ammonium sulfate. Okay, you see the balanced reaction. You always have to make sure that you have the balanced reaction in front of you. And if it's not balanced, you have to take a minute to balance it. So this is the balanced reaction. And you're told that you start with 1,000 grams of ammonia. And the question is, how much, what mass, how much of sulfuric acid would you need to completely react with 1,000 grams of ammonia? What do? The same thing. You have to convert the mass of ammonia to moles and then make a mole-to-mole comparison. So 1,000 grams of ammonia, if divided by the molar mass, which is 17 for ammonia, gives us 58.8 moles of ammonia. How many moles of sulfuric acid would we need to completely react with that many moles of ammonia? Well, if we look at the stoichiometric relationships for this problem, for every 2 moles of ammonia, we need 1 mole of sulfuric acid. Or in other words, we'll need half as many, so we multiply by 1/2, half as many moles of sulfuric acid as the number of moles of ammonia that we started with. So that would be 29.4 moles of sulfuric acid. That's how many moles we would need, half as many as the number of moles of ammonia. Pretty clear. If we're asked how much, what mass, we then multiply the 29.4 moles by 98 grams per mole. Okay? Now take a look at this and see if it all makes sense. Now we'll pause, and in the next video lesson we'll go into a number of other examples of stoichiometric problems. See you in a while.